Hello, good morning all of you. So we have started our new topic, that is asymmetric synthesis. In previous lectures we have seen that what is meant by asymmetric synthesis, then chiral pool, chiral auxiliaries, strategies, then chiral catalyst. Okay, in previous lecture we have also seen the asymmetric hydrogenation reaction as well as asymmetric epoxidation, that is Sharpless asymmetric epoxidation, and Jacobson manganese saline asymmetric epoxidation. Okay, now today we are going to see the details of Sharpless asymmetric dihydroxylation. Okay, so it is actually well known by all the organic chemists that this dihydroxylation is known by asymmetric dihydroxylation, and this process is also invented by the scientist Sharpless. Okay, now what is this? Dear students, we know that if it is a carbon-carbon double bond, that is an alkene. Okay, and if we want a syn addition reaction resulting into the formation of 1,2-diol, okay, like this 1,2-diol, or like this. So we generally used the two reagents, and that two reagents we know that one is alkaline KMNO4 in presence of alkaline, that is alkaline medium KOH, aqueous KOH or aqueous NaOH, or the second reagent is OSO4, that is osmium tetroxide. Okay, but as we know that this KMNO4 is a very strong oxidizing reagent, so that's why it has some limitations, as well as this osmium tetroxide is volatile in nature and it is toxic in nature, so that's why these two reagents have some limitations. Okay, but they are widely used in the synthetic chemistry or in organic chemistry because they gives the desired product, that is syn diol or syn glycol, either or we may get the racemic mixture of these two. Okay, so a simple alkene, when we start with simple alkene and if we use these reagents, then we may end up with the racemic mixture of syn diol. But if we want a enantiomerically pure or enantiomerically excess syn diol product with controlled stereochemistry, then we should think about asymmetric dihydroxylation. Di means two, hydroxylation, so two hydroxyl groups are get attached, are get bonded, are get introduced to the carbon-carbon double bond, across the carbon-carbon double bond. Okay, so this is the well-known reaction of use of osmium tetroxide. Okay, so see this reaction, this is a 5-decene, and in this reaction we have used their catalytic osmium tetroxide. It is just used in catalytic amount. Okay, the water and tertiary butyl alcohol are used as solvents, and plus along with these two, one chiral reagent is used or one chiral ligand is used. Okay, so this reaction of this alkene, with the help of these reagents, we end up with the such syn diol. Both hydroxyl groups are beta or above the plane. Okay, and we are getting this molecule or this product as 97% enantiomeric excess. Okay, means this product is forming in 98.5%, and the other isomer of this other diastereomer of this molecule is forming 1.5% only. Okay, so how this enantioselectivity can be obtained? Okay, so this is the main basic idea of using this chiral ligand. Okay, and in this case the R and R dash groups are the side chains of this carbon-carbon double bond. Okay, so what is the main basic here? See, osmium tetroxide is used in only catalytic amount, and the water and tertiary butyl alcohol are used as a solvent, and the main the basic idea or the key point or key role is of the chiral ligand. Now, as this osmium tetroxide is used as is used in very catalytic amount, so there must be some reagents. That reagent is oxidizing, that is converting that osmium which is produced at the complete reaction cycle. Okay, so that osmium tetroxide is get regenerated in the reaction mechanism. So such reagent must be present in this reaction mechanism, so that we can get, or we require a very little amount of catalytic amount of osmium tetroxide. Okay, generally this is satisfied by the K3FeCN6. K3FeCN6. So this reagent K3FeCN6, potassium ferrocyanide, is used as a conversion of this catalytic amount that we are using here, osmium tetroxide, and that this osmium tetroxide is in +8 oxidation state. Okay, so when elemental oxygen is get generated in the at the end of reaction mechanism, then osmium is get converted into osmium 8 during the reaction mechanism, and this work is done by the potassium ferrocyanide K3FeCN6. Okay, so this is used as a co-catalyst for the conversion of osmium. Now, what about the chiral ligand? So, what about the osmium tetroxide? Osmium tetroxide is generally not introduced directly into the reaction mixture. Okay, instead of that, it is used as K2OSO2OH4. Okay, so this reagent is used instead of directly using osmium tetroxide OSO4. This reagent is used, and in this reaction mixture this is the source of osmium, and with this water and tertiary butyl alcohol and all these things, the OSO4 is regenerated. OSO4 is generated in situ in the reaction mixture. Okay, so these are the sources of osmium. Now come to our main point, that is chiral ligand. So which chiral ligand is used here? So the chiral ligand that Sharpless used in this reaction is the dihydroquinine, and second one is dihydroquinidine. Okay, dihydroquinine and dihydroquinidine. Okay, so these are the chiral ligands that the Sharpless is used for this asymmetric dihydroxylation reaction. Okay, so see these dihydroquinine and dihydroquinidine, these are the structures of these two chiral ligands. Okay, so when we are looking carefully these two molecules, then they are not the actual enantiomers of each other. Okay, so when this is oxygen and there is a bond between oxygen in this aromatic ring, when this H is equal to aromatic ring, when this aromatic ring instead of Ar, when it is hydrogen is there, then this molecule is called as DHQ, and when again in this molecule, when this instead of Ar, when it is hydrogen is there, then this molecule is called as DHQD. Okay, so these reagents are known as chiral ligands. Okay, so they are the alkaloids that can be used as a chiral ligand for this asymmetric dihydroxylation. Okay, now these DHQ and DHQD are get attach, or they can couple with this phthalate based ligands. So these are the structures of phthalate. Okay, and when the two molecules of this DHQD is get attached to this phthalate, then the resulting structure is called as DHQD2 phthal. DHQD2 phal. Okay, so this is the structure of DHQD phal, and when two molecules of DHQ twice phal is nothing but two molecules of DHQ are get attached to this moiety, okay, thalazine moiety, then it is called as DHQ2 thal. Okay, so these are the alkaloids derived from the natural source and they are used as a chiral ligands for the dihydroxylation reaction. Now what happens when we are using here, when we are using the chiral ligand? What is the actual chiral ligand here? When we are using DHQD, when we are using DHQD as a chiral ligand to the thalazine, then we are getting mostly the beta hydroxy group on the adjacent carbon atom of carbon-carbon double bond. Okay, so this is the main source, DHQD. When we are using DHQD, then we are getting 97% enantiomeric excess of this diol, 1,2-diol, and these both of hydroxy groups are coming from the same side of the carbon-carbon double bond, that is they are from the above the plane, or they are from the top face of the carbon-carbon double bond. Okay, so that's why we are getting enantiomerically excess of this isomer. Okay, but when we are using DHQ, when we are using DHQ, that is dihydropyridine, okay, then we are getting here, alpha hydroxy groups. No doubt both alpha groups are alpha, so that's why in both of the cases we call it as a syn dihydroxylation. And why it is called as asymmetric dihydroxylation? Because we are getting one diastereomer very high proportion as compared to other, so that's why such reaction is called as asymmetric dihydroxylation using chiral ligand based on thalazine based ligands. Okay, and the ligands, thalazine based ligands, are generally DHQD and DHQ. Okay, then the general reaction that can differentiate the use of this DHQ and DHQD can be taken as a stilbene. Okay, so we know that stilbene is 1,2-diphenyl ethylene. Okay, so this is carbon-carbon double bond, this is pH, this is also pH. Okay, so this is what? Trans-stilbene. So this is a very specific example of which explains the enantiomeric selectivity of this reaction. Okay, so this is trans-stilbene. Now when we are using our general reagents, that is this catalytic OSO4, then this K2OSO2, sorry, this OSO4 is generated, they are directly taken OS, K2OS, O2, OH4, okay, source of osmium, then K3FeCN6, K3FeCN6, okay, co-catalyst which is converting this osmium to osmium 8, then a base K2CO3 potassium carbonate, then methane sulfonamide SO2NH2. Okay, this is used to increase the rate of reaction, and one catalyst used here, DHQ2 phal. Okay, now this is trans-stilbene. The stereochemistry is both of the phenyl groups are trans anti to each other, so this stereochemistry is retained in the product, and we are getting here, this is product pH aromatic ring, phenyl rings, and as The chiral ligand is DHQ2 fall. DHQ2 fall. So we are getting here alpha hydroxy groups. Alpha hydroxy groups. So both hydroxy groups across the carbon-carbon double bond are get introduced, which are coming from the bottom face of the carbon-carbon double bond. Okay, so this is the main product, and we are getting here 97% in enantiomeric excess. Keeping the all things same, all these things, the things or the reagents that we have circled here, all these things are same reagents. Okay, except one, and that one is the chiral ligand. Instead of using DHQ twice phal, we can use here DHQD twice phal. So when we are using DHQD twice phal, the result is reverse, and we are getting pH, and the hydroxyl groups are beta. Hydroxyl groups are beta to each other. So both are beta. Okay, so they are, both of the hydroxyl groups are coming from the top face of the carbon-carbon double bond. Okay, so this is, we are getting 99% enantiomeric excess. We are getting 99% enantiomeric excess. So the stereochemistry is written, and the upcoming or incoming hydroxyl groups are coming from the same face of the carbon-carbon double bond, and here they are coming from the top face, so we are getting beta hydroxyl. So this is an example of asymmetric syn dihydroxylation using osmium tetroxide as a source of this is the reagent, and these are the two chiral ligands which are helpful for getting the asymmetric product. Okay, so these are the two main examples that can differentiate how that asymmetric dihydroxylation can be achieved. Okay, now we will take some more examples based on this. Now the examples are, so let us say this is para-nitrophenyl group, and this is a carbon-carbon double bond having CO2 ester, alpha beta unsaturated ester. Okay, and the para-nitrophenyl group at the beta carbon. Okay, so when OSO4 catalytic amount of OSO4 osmium tetroxide is used, then remaining reagents are same that before reaction, K3 FeCN6, then potassium carbonate K2CO3, then DHQD containing ligand. So this information is given, and we have to ask the what will be the product with correct stereochemistry. So we know that all these reagents required for the dihydroxylation reaction, and the ligand is used here DHQD containing ligand. So it may be thalazine based or other based reagents may be used, but what is the important here? DHQD is given. So DHQD is given, so hydroxylation is taken place from the carbon-carbon top face of the carbon-carbon double bond. So my product will be all things remaining same, and the product is this one, CO2 So this is the product, OH. Both hydroxyl groups are from the top face of the carbon-carbon double bond. So beta 1,2 diol. Whatever the IUPAC name or the other name of that compound, whatever it may be, we can assign the name, but what is important? The stereochemistry is important. Okay, so this is the important. And once if you use here only DHQ containing ligand, if the reaction or the problem is asked like that, DHQ containing ligand, so the stereochemistry is get reverse here, and we get here alpha hydroxy, alpha 1,2 diol. We are getting alpha 1,2 diol. Okay, so this is the main difference of these reagent. One more example is there. So let us see the problem. So the product that we obtained here can be used in the synthesis of chloramphecanol. In the synthesis of chloramphecanol. Okay. So I am writing that reaction for the synthesis of chloramphecanol, COUT, then hydroxy group, para-nitro group. So that product, this product we are getting in the previous reaction. Okay. Then what they have done here, tosylation, tosyl chloride, okay, and triethylamine, NET thrice triethylamine. So what is happening? We are getting here triethylamine. So tosylation of hydroxy group takes place, and the H and Cl will be neutralized by the triethylamine formed in this reaction. Okay. So this is the product. CO2 ET. Okay. Then LiLH4, so LiLH4 is used. This will reduce this COET group. Into CH2OH. The next step is attack of azide, sodium azide, Na(N3), sodium azide. So this is epoxide, N3 minus will attack on this carbon, and the epoxide ring will get open. Para-nitro group is as it is. So we are getting hydroxy beta CH2OH, and we are getting here N3. Okay. Now then the next step is reduction of this N3 reduction. So when we are getting reduced this N3, we are getting NH2. Okay. And once we are getting this NH2, the next step is use of Cl2 CH CO2Me. Okay. So this ester is there. The structure of this will be like this: Cl2 CH COOMe. So this ester is there, and when this lone pair of nitrogen will attack on this carbonyl, methoxy group will be knocked out, and the product will be like this: para-nitro with hydroxy group at beta, and NH will get attached to this carbonyl, COCHCl twice. Okay. And this group is attached to CH2OH. Okay. So this is the product, and this product name is chloramphecanol. The product name of this is chloramphecanol. Okay. It is used for the in the drug. Now at the last we can conclude how this all happening. Okay. So by treating this carbon-carbon double bond with two phases. Let us see. R, R dash, R double dash, R triple dash, etc. or hydrogen, let's say. You can take any one. Okay. So some R groups, alkyl groups are smaller, some alkyl groups are larger, etc. Okay. So when DHQD, is the chiral ligand, DHQD containing chiral ligand is there. So then dihydroxylation takes place from the from top phase, okay. And when we are using DHQ containing ligand, then dihydroxylation takes place from bottom phase. Okay. So this is the summary of sharpless asymmetric dihydroxylation. Okay. So keep in mind that only one difference is that DHQD and only DHQ. Okay. So when DHQD is there, dihydroxylation from top phase of the carbon-carbon double bond, and from when we are getting when we are using DHQ, then we are getting dihydroxylation from the bottom phase. Okay. So thank you very much for joining this and seeing this video. Have a nice day.